AI coding agents can now write thousands of lines of working software in a matter of minutes, but a human still has to read it. This verification asymmetry pits a massive, strong model churning out vast code against a tiny, weak model auditing the perimeter. Researchers tested this by deploying a small reviewer model, Gemma 4E4B, to inspect a Python repository hiding exactly 11 backdoors. This chart maps the reviewer's success rate at finding those threats. Operating under standard conditions, the small model caught 54.5% of the backdoors. But by restructuring the environment it was working in, researchers pushed that recall rate to 90.9%. Securing high-stakes AI pipelines does not require building larger, more expensive reviewer models. True oversight requires changing the structural rules of the codebase itself. The industry's default approach to keeping agents on track relies heavily on prompts. Developers use systems like the Model Context Protocol, or repo maps, to load huge amounts of project architecture directly into the language model's context window. But this introduces attention dilution. As the context window fills with raw code payloads, the models focus on the core instructions degrade. They blur and fade into the background noise. Beyond distraction, LLMs treat prompts as advisory. A prompt is a suggestion, not a mathematical absolute. Once an agent has terminal access, instructions can be overridden by indirect prompt injection, leading to silent drift in codebase guidelines. The researchers propose an alternative mechanism, steerability via substrate constraints. You cannot steer autonomous agents reliably with polite prompts at the interface layer. You must deploy mathematically enforceable constraints directly at the code level. To implement these substrate constraints, we have to look back at the pre-LLM software engineering tools that human teams have used for decades. This matrix outlines the shift. On the left is an unconstrained codebase, populated by standard Python defaults. On the right, the constrained architecture. This stack uses rough for linting, JAX typing for tensor shapes, and bear type for runtime checking. To lock down runtime behavior, the stack also integrates Pydantic in strict mode and enforces the use of frozen, immutable data classes. The philosophy driving this stack is strict locality. The AI is forced to write verifiable code where rules are checked and enforced by these tools before the script even runs. A standard agent has to hold complex behavioral rules in its working memory across thousands of tokens. This architecture offloads that cognitive burden to the compiler. By utilizing substrate constraints, architectural contracts become textually visible directly within the source code. Deterministic tools physically refuse to execute code that violates the spec, regardless of what the user prompt requested. This raises a practical challenge. How do you give an agent enough context to understand the repository without saturating its context window? The answer is the projection principle. Agents do not need raw implementation details for every file. They need a topological map of the code structure. The researchers implemented this using a lightweight command line interface driven by abstract syntax tree parsing. Instead of feeding the agent entire files, this tool extracts exactly two things: the module's public API and its documented invariants. This lazy loads the context on demand. It avoids the model context protocol's tendency to saturate the agent with massive, irrelevant text payloads. This localized, symbol-specific view perfectly mirrors how human engineers conduct pull request reviews in production. They look at isolated function blocks, not the whole repository. Providing the AI with exactly the context it needs, and mathematically nothing more, isolates the review environment and tightens security. To see this failure in action, we can run a forensic autopsy on one of the injected threats, the L5C streaming aggregate backdoor. The threat vector here is specific. It is a bug that behaves perfectly when fed clean, sorted benchmark data, but executes a malicious payload the moment it encounters unsorted data. This code editor displays the unstructured implementation of the aggregate function. It contains the malicious loop, topped by a vague, single-line docstring. The global rule that governs this specific function's safety does exist, but it is trapped in a centralized architecture markdown file at the root of the repository. A local reviewer agent inspecting the specific function block has no visibility into that global rule. Without the rule, the code looks benign, and the agent approves the backdoor. This is exactly why the unstructured architecture only caught this class of backdoor 54.5% of the time. When critical behavioral constraints are physically separated from the code they govern, localized AI oversight breaks down. Now we look at the constrained version of that exact same aggregate function. This split screen compares the two. The right side introduces explicit mapping types and a rigorous invariant block directly in the docstring. The text dictates the function must consume scores in any order. The malicious loop below directly contradicts that invariant. The logical contradiction is no longer hidden across multiple files. It is entirely textually visible to the reviewer in a single pass. The 8 billion parameter model does not need deep contextual comprehension to spot this. It only needs to compare the adjacent text. Under this configuration, the exact same reviewer model caught 90.9% of the backdoors. Shifting the verification burden from open-ended architectural comprehension to bounded, localized invariant checking makes scalable AI oversight mathematically achievable. High recall is useless if the system flags every line of code. We have to address precision, which measures the risk of false positives. This data table highlights a phenomenon called the precision tax. When researchers enforced code constraints but removed the CLI projection tool, the reviewer model began inventing rules and overflagging clean code, dropping precision to 88.9%. It is the combination of the constraint substrate with the local CLI projection that restores precision to 95.7%, keeping the false positive rate low. This flowchart maps the final start-to-end architecture. The AI agent operates inside an isolated virtual machine, with network egress strictly filtered. All model calls route through an inference proxy. This intercepts every prompt and response, passing them through semantic probes to block prompt injections and policy violations at the network boundary. True steerability relies on this synthesis. You isolate the agent at the machine layer, and you constrain its output at the codebase level. Enterprise AI coding pipelines that rely entirely on prompt engineering to govern security will drift, hallucinate, and accept malicious logic. To maintain control over automated generation, developers must return to the strict deterministic disciplines of pre-LLM systems engineering. These methods require fewer tokens, execute faster, and offer mathematical resistance against code insertion that language models simply cannot bypass. The verification of an AI agent belongs in the immutable substrate of the code itself. It never belongs in the advisory text of a prompt.